and a half, as you might have guessed, but we have a lot to look forward to. So I'm going to go ahead with my spiel, and I'll keep reminding folks that join us to drop their name and where they're tuning in from in the chat box. So welcome to Laguna Wetland Geology Through Time, a webinar with Nicole Myers. My name is Allison Titus, and I am the Community Education Manager at the Laguna Foundation. This will be my last community education webinar with the Laguna Foundation, and I am thrilled to be spending it learning about geology and hydrology, the foundation of the Laguna watershed. The Laguna sits within the homeland of the Coast Miwok and Southern Pomo people. To raise awareness for the ancestral and current Indigenous peoples' presence in the Laguna watershed, we pay our respect to the past, present, and future generations of Coast Miwok and Southern Pomo people and their Wapo neighbors. If you'd like to know more about the Indigenous land you live on, you can visit nativeland.ca. I'll drop the link in the chat. It's a great resource to start learning about where you live. All right, so a little bit more about the Laguna Foundation. We are a nonprofit organization based in Santa Rosa that works to restore, conserve, and inspire appreciation for the Laguna de Santa Rosa wetlands. The Laguna is a wetland and a 22-mile-long waterway, as well as an entire watershed, which you will be able to visualize more clearly here shortly. We'll have lots of maps in this presentation to help you understand the bounds of the watershed. But that watershed encompasses Santa Rosa, Cotati, Rohnert Park, and parts of Sebastopol and Windsor. The Laguna wetlands have been heavily impacted by development in the Santa Rosa Plain, and they now face important issues that drive our restoration, conservation, and education work today. But those impacts is not the whole story. Despite those challenges, the Laguna is a biodiversity hotspot, home to endangered plants and animals, and has the very special designation of being a wetland of international importance. It is one of only 34 sites in the United States with this honor. We restore these special wetlands by completing conservation science projects like planting native trees, shrubs, and flowers, and managing invasive species. And we increase public knowledge and appreciation of the Laguna through our Learning Laguna Elementary School program, our Camp Thule Summer Camp, and community programs like this webinar today. Thank you to those of you that included a donation with your registration for this program. It is much appreciated. Our organization relies on donations from individuals like you to continue our critical restoration, conservation, and education work. You can also donate securely on our website, and I will include a link to that in the follow-up email. If you enjoy this program today, we have many more coming up this fall, so check out our community education page on our website for more information on upcoming events. I want to remind you all that this presentation is being recorded and will be available to view on our YouTube channel by this Friday. You can view it on our YouTube channel. You will also get a direct link to the recording in your email from Eventbrite, the same way you got the link to join the webinar today. And without further ado, it is my pleasure to introduce our speaker for today. Nicole Myers developed a passion for understanding the Earth from a childhood fascination with rocks and volcanoes, which I can also appreciate because I grew up at the base of a volcano in Mount Shasta, California. She now teaches others to appreciate planet Earth. She has a master's in geological sciences, and she has been teaching earth science classes, including geology, climatology, and earth history for more than 15 years. She currently teaches at Sonoma State University and through Appreciating Earth. Nicole, thank you so much for being here with us tonight to teach us about this critically important piece, increasing our knowledge of the Laguna. I will hand it over to you to get started.
Thank you so much. I'm so excited to be here. I'm going to get my screen going for you. And it is true, there's a lot of maps, but anyone who's seen one of my talks, you know I love my maps. The geology of Laguna de Santa Rosa. What I find so interesting about looking at really the Santa Rosa Plain area and how water has flowed is it's completely connected to the underlying geology. So we can learn a lot about Laguna de Santa Rosa hydrologic network by really understanding what it is upon and how water flows towards it. So we're going to start with a little bit of topography. See, 3 maps already. Here we have on the right side, the Laguna de Santa Rosa watershed. Now, every time you look at a watershed map, it's going to be slightly different because each person who draws a map will define the term watershed in a slightly different way. So you're going to see probably 6 different watershed maps, all of which have much in common, but also have slight differences. So through here on the left side, I'm going to draw it over in red. This is what we would technically consider the Laguna de Santa Rosa in terms of hydrology. But notice all of these blue lines that flow into it. All of this is rivers and other waterways that bring both water and sediments into Laguna de Santa Rosa. One of the things I want to note is that Laguna de Santa Rosa is oriented northwest-southeast, which is the same orientation as the Sonoma Mountains to the east, as well as the coastal mountains to the west, and of course, the Santa Rosa Valley itself. In fact, if we look at the western edge of California and most of California in general, almost everything topographically is subparallel in the northwest-southeast direction, which also happens to be the orientation of the San Andreas Fault. Technically, the San Andreas Fault system, which the San Andreas Fault is part of it, not only created this topography, but is also responsible for the overall shapes of the watersheds, the mountain ranges, and the valleys that we see today. We understand today that there's so much underlying complexity when it comes to attempting to understand how the Santa Rosa Plain came to be as it is today, and why the water flows towards the western side of the Santa Rosa Plain. Like, why does Laguna de Santa Rosa exist? Laguna, of course, means lake. So this is literally the Lake of Santa Rosa. Where did that name come from? And how has it changed really over the last couple hundred years so that many of us don't even recognize it as a lake today? So as we go over to the middle map, this map is an elevation map of the Laguna de Santa Rosa. So you can see those areas that are in the lightest blue. Those are the lowest in elevation, the places to which the water is going to flow. And then we can see how that elevation increases through greens, yellow, orange, red, and into the browns and then grays. These topographic elevation maps are really, really helpful because we use them to inform us of when there might be a flooding issue. And since the Laguna de Santa Rosa is quite literally a wetland, it is also a floodplain, and therefore we should be prepared for future flooding. So this floodplain map here on the left side of the screen, this is really showing the extent to which water will cover the surface area of the Santa Rosa Plain, and of course the Laguna de Santa Rosa during a high flood event. We can see that the flow of water from east to west, pooling on the west or the left side of the valley, is really what creates the Laguna de Santa Rosa. It's filling in these lower elevation areas that we can see on this map. So one of the things we want to understand today, excuse me, is why is the valley lower in elevation on the west side? Why don't we see water pooling over here on the east side? What is it about the underlying geology that has created the whole valley to dip just a little bit towards the west so that the water flows in the direction of the dip? So we kind of need to start the story, the geologic story, by going really far back in time. We need to understand what rocks exist on the surface at this point in history, where those rocks formed, and how they affect the Laguna de Santa Rosa. So I start with one of our most simple geologic maps here. It's simple only because we group so many rocks. Oh my, I'm losing my voice. Excuse me. We group so many rocks together and we put them into terrains. So you can see that the word terrain is spelled a little bit differently than we normally spell the word terrain because it is a geologic term. So we see in these diagonal lines that I highlighted here in red, those are rocks that formed in an oceanic environment. And those rocks in that oceanic environment are what we call the Franciscan complex. They're in this turquoise color in the bottom right map. So part of what we want to understand is, where did these rocks come from? How old are they? And how do they help to shape the Laguna de Santa Rosa? The other rocks that we need to be aware of is the cover terrain. That's in this just general white color. And we also see cover terrain on this map on the bottom right. It's what we see in this orange color and in the gray color and in the white with dot colors. Cover terrain is really just saying relatively recent rocks, as in laid down on the surface of the earth relatively recently and are covering up that which is older, that which came up or was uplifted from below. And in fact, when we look at the Franciscan Formation, which is marine in its origin, the Laguna de Santa Rosa is upon that basement rock. We call it the basement rock because it is the deepest rock. And that Franciscan Formation formed upon uplifted and eroded marine sediments. So one of the first things we have to do to really understand Laguna de Santa Rosa is understand what was the overall topography and the continental shape like when these oceanic sediments were being laid down on the surface. Where was the coastline? Because if what we're calling Laguna de Santa Rosa today was part of the ocean, we know that the coastline was not here. It was actually further to the east. So we're going to use these sediments to investigate changing coastlines. Another really important part of the story is those sediments are mantled by volcanics. That's what this orange color here is, with the kind of V shape. Those volcanics erupted on top of and were overlain on the Franciscan Formation. We also understand, as noted before, that water is draining to the lowest elevation. So why is it that the lowest elevation for this valley is on the west side of the Santa Rosa Plain? And in fact, why do we oftentimes in California, not all the time, but often, see that the low side of the valley is on the west side? What is it that these valleys of California have in common that cause more drainage to pool on the west side of valleys? Even here in this center map, this is a historic and current extent of wetlands map for this Central Valley of California. And you can see in red is where the wetlands are. And notice that there is generally a little bit more pooling of the water towards the west side. And that's because both the Santa Rosa Plain and the Central Valley have this little bit of a tilt. So the east side of the valley is just a little bit higher in elevation. The west side is just a little bit lower. And that directly affects the way water flows, the formation of wetlands, and of course, then what sediments are laid upon the surface of the earth. So for me to go any deeper into this, I kind of at least need to introduce the three rock types. For those who are already well-versed in geology, you may know this, but I'm not going to make that assumption. We have three rock types: igneous, sedimentary, and metamorphic. Every rock on this planet and beyond can be put in one of those three categories. So an igneous rock, aka volcanic, is a rock that formed as a result of magma cooling. So it's the solidification of magma. That's going to be important for today because we find igneous, aka volcanic rocks, within Sonoma County. And as those volcanic rocks are eroded, as they break up on the surface of the earth in those broken pieces, they flow from east to west, they become part of the sediment base that fills up Laguna. So we do want to understand their origin and understand how that affects the Laguna overall. Now, any kind of rock that is broken into pieces and those pieces end up in contact with the atmosphere. So wind and water, UV radiation, everything just kind of breaks up that surface material. Those weathered rocks that have been weakened by that atmospheric connection, they end up moving or being eroded. So the weathering is the actual breaking up or changing of the surface rocks, and erosion is the movement of those surface rocks to a new lower elevation location where they become deposited. So erosion is going to be, especially in this region, it's going to be really dominated by water. Water is going to be the main eroder, that which carries the sediment from high elevation to the relatively low elevation of Laguna de Santa Rosa. And as that sediment finds a low elevation area to deposit in or to settle in, it ends up layering up. And those layers, they get buried. And as they get deep enough for the broken pieces to get cemented together, they become our second rock type, sedimentary. Well, our Franciscan Formation, which came from our marine environment, it's sedimentary. So that's why this is also a really important rock type to understand for this region. It forms by the burial and the compaction of transported matter, really just broken pieces of rock. We're not going to be surprised that if we have lots of volcanic rock on the surface, like in Sonoma Mountains, as that volcanic rock breaks up into pieces and moves through the waterways to become part of the laguna, we end up with a lot of volcanic remnants within the laguna. Our third rock type is metamorphic. Now, metamorphic rocks are a little less important to today's story, but certainly not important to the Earth story. Metamorphic rocks are the alteration of pre-existing rocks due to increased pressure and temperature. So it's really going to be deep burial is going to be the main way that those rocks form. I'm going to ignore metamorphic rocks for this talk from this point forward. The other thing I wanted to introduce you to is the geologic timescale. So I'm going to make sure I don't spend a lot of time talking about different periods and eras and eons of geologic time, because I have to assume most people are not as well versed in the geologic timescale. But some of the terms that I will be saying today are things like quaternary, especially when we look at Q on our map. So quaternary is essentially most recently formed rocks. I'll also probably talk about the Mesozoic. When I say Mesozoic, just think time of the dinosaurs. Those are going to be the most commonly used, but again, I'm going to try not to use these terms too much. But essentially what the geologic timescale is the geologist's way of breaking up Earth history into segments so that we have a way to communicate with each other what we mean by certain segments of time. Just like if I say, let's meet up in July, you and I know that July is in the summertime for the Northern Hemisphere. We know where it is in time. We agree what July means. Just like when geologists say, that formed in the Triassic, we know what span of time we're talking about. It informs us of chronological order, especially of geologic processes. So when we start in our chronological order, of course, I'm going to have to start with that basement rock, that Franciscan complex. That Franciscan complex is oftentimes referred to as Franciscan Formation. They're essentially the same thing. Geologists really like jargon. We have a lot of words, like there's a lot of words in geology, and we sometimes change our mind as to what word means what. And recently we have changed from formation to complex, and there's reasoning behind that I will not bore you with. So how did this Franciscan Formation form in the first place, or this Franciscan complex? We're going to have to go back in time to at least 140 million years ago, though some of the rocks that are part of the Franciscan Formation date back to 190 million years ago. So we're going pretty far back in time. And we know that as we go back to this period of time that we call the Mesozoic, that the west coast of California, as we know it, looked very, very different. So here we have the North American plates. It's in brown, and you can see the Sierra and Arc. The Sierras, in fact, are volcanic in their formation. And then we have another plate. So in geology, we look at how the surface of the Earth is broken up into plates. We call them tectonic plates. And those plates are moving relative to each other. Here on the bottom left map, we have an example of a divergent boundary. So divergent boundary means to pull apart from each other. And in this video, which I'll stop and start a couple times, this gives you a really sped up idea of what a divergent boundary is, that we have hot rock coming from below, rising and then splitting in convection currents and pulling two plates apart from each other. When that takes place, volcanic rocks come to the surface to fill in that gap. So anytime that we are looking at a divergent boundary, we're also looking at volcanism. Now, that oceanic plate that was formed at that divergent boundary, this one we call the Farallon plate. And this Farallon plate of the past, it moved eastward. And on top of that Farallon plate, there's volcanoes, there's islands, there's all kinds of stuff. There's mud and sand, all the stuff that rides upon an oceanic plate. And then the Farallon plate met up with the North American plate, moving in opposite directions, they converged. And the oceanic plate, as it always does, because it's denser, it subducts. It goes down, it sinks below the less dense North American plate. And upon doing so, it gets hotter and hotter as it gets closer to the Earth's core. Magma forms as that rock melts, and then that magma rises to the surface and fuels volcanoes. Well, this volcano is supposed to represent the Sierras. So we're looking at a time back in the time of the dinosaurs where the Sierras, as you and I know them, did not exist. Instead, it was a line of volcanoes, very similar to the Cascade volcanoes to our north. We call this an ocean continental subduction zone. And back to that video in the bottom right, you can see what that subduction might look like, how the divergence leads to the subduction. And we're just about to zoom into one of those subduction zones. And one of the things I want you to consider is what's happening at that subduction zone. It's not as smooth and simple as it appears here. Instead, there's scraping off of the surface oceanic material that would be taking place. And that scraping off creates what we call an accretionary wedge. This thing in blue, that's the accretionary wedge. That's literally surface material scraped off. That is what the Franciscan complex is. The Franciscan complex is an accretionary wedge. We are standing upon, for those of us who are in the Western California area, we're literally standing upon the material that scraped off an oceanic plate as it dived down. We are standing upon ancient rocks that were left behind by the process of subduction. Now, that process of subduction, it changed in Western California quite a bit. So this is a series of maps that was created to give us an idea of how the West Coast changed. I'm going to go through them pretty quickly, though. So this is showing 60 million years ago, and the star shows us essentially where Sonoma County is, in the middle of the ocean. Franciscan Formation is still being deposited. Same is true 50 million years ago. This dark line you see here, that's the subduction trench. Volcanoes would have been erupting essentially through here. Now, as we get towards 30 million years ago, something changes. And what happens is to our south, closer to LA, a new plate comes in from the west. So here we have the Farallon plate in blue, North American in brown, and here comes the Pacific plate. And as the Pacific plate meets the North American plate, subduction where that meeting has taken place ceases. And the San Andreas begins to form. The San Andreas transform boundary essentially formed starting 30 million years ago, but it didn't make it up to Sonoma County until sometime just after 20 million years ago. So we go forward to 20 million years. MA means million. Notice here we have that star, and right here, this is the northernmost extent of the San Andreas. But starting about 20 to 15 million years ago, as the San Andreas approached Sonoma County region, all kinds of transition took place. The crust was torn and rent by this process of changing from subduction to transform. So transform is when two plates slide past each other. They might be going in the same direction or in opposite directions, like cars on a freeway, but cars touching each other, which is generally what we don't want on a freeway. As a result of that tearing of the crust, volcanism occurs. And that volcanism dates back to about 12 to 2 million years ago in this region. By the time we get to 10 million years ago, you can see that this region has changed quite a bit. So this is the origin of the rocks that make up a lot of the mountains to the east. I will definitely be getting to questions towards the end of the talk. So I see hands raised and I see chat questions in. I'll definitely just kind of get to all those questions towards the end. So we now have this point in the story where the San Andreas exists. We've changed from subduction in this region to now mini faults. We tend to like simplify the number of faults, but let's say thousands just to be realistic here. All of these faults that we see on this map, they're all part of the San Andreas system. The system itself is the tectonic boundary. The Pacific plate is moving northwestward, and very technically, the North American plate is also moving northwestward. It's just that the Pacific plate is moving faster. So it's like two cars on a freeway where one pole is ahead of the other, but those two cars are squeezing into each other. And as they squeeze into each other, it buckles the rocks and creates all kinds of faults, causing some areas to rise, become mountains, and others to sink and become valleys. Here on our left-hand map, we start to see the result of all of that collision that leads to cracks in the crust. And along those cracks, magma from the mantle below rises. We can see that it came up in kind of spurts. So we have relatively old Mount Burdell volcanics, closer to 11 million years old. We have TV for Tolle volcanics, that's kind of in the red. That's directly underneath and adjacent to the Laguna de Santa Rosa. And then we have the Western Sonoma volcanics. Those are in orange. The Eastern Sonoma volcanics in brown, and the Northern Sonoma volcanics are in yellow. So the volcanism didn't happen all at once. It literally was a result of faults forming during this transition. Those that affect the Laguna de Santa Rosa in particular would be the West Sonoma volcanics that were erupting between about 8 to 4 million years ago, and the Tolle volcanics that were erupting closer to like 10 to 8 million years ago. So they kind of overlap each other. I want to note that right here, there's the Laguna de Santa Rosa. So we can see that it's bounded by mini faults. Now you've seen a lot of maps already, so you're not surprised, but we have to add more complexity to these maps because it's not just volcanic rocks that make up this region. In the left-hand map and in the right-hand map, what we see in pink, that's the volcanics. While all this stuff in orange and in yellow and in light greens, that's all sedimentary rocks. And we end up using a lot of different maps because there's no one map that can give us 100% of the information. There's just too much. So each map kind of has a purpose, and it's going to show us whatever the map maker thinks is most important. So there's a few things I want to point out as being important here. Notice here we have a Sebastopol fault. So that's on the west side of the Laguna. We also can see here this kind of green area. This is showing the direction that sediment flows into the Laguna. But we also have another fault here, and that fault is causing some uplift on this side, therefore making the Laguna here just a little bit deeper. So the reason the Laguna is the deep point of our valley is that really the faults are causing a little bit of uplift, more uplift to the east, and down dropping on the west. Therefore, we end up with this basin or this bowl that the water can accumulate within. Now, when that water accumulates, it's never just water. Anyone who has seen or experienced flooding knows that water is never pure. It's very dirty. There's a lot of stuff in water. And that water, with all that sediment, is going to essentially flow to a low point and deposit whatever sediment is within it. That might be mud, it could be sand, it could be pebbles, there could be fossils in it, there could be plants. Whatever is being deposited is really showing us what flowed to that point of deposition. So sediments, we say, are reworked by water and gravity. So remember that geologic time scale? And I said I'm going to be coming back to Q. Q is for Quaternary. Quaternary is the most recent span of time that we are all currently living within. And we can see that there's quite a bit of Q on this map. So yet another map with a different purpose. But now we can see the Laguna de Santa Rosa with a little bit more detail. So we have QGE, that's in yellow. We also have just Q in kind of a lighter yellow. That's all very recently formed sedimentary rocks. Those sediments have been essentially carried by rivers from east to west. And some of that sediment, especially in the light Q color, have allowed the Laguna de Santa Rosa to slowly fill in. Now, it's not just natural processes that have caused Laguna to fill in, as we will see. But one of the things that happens is alluvial fans form. So here is an alluvial fan. This is not in Sonoma County. This is in Death Valley, because alluvial fans are much easier to see in the desert. Essentially, what happens is when rivers leave the mountains, those rivers are moving fast. They are carrying a lot of sediment. They have what we call big sediment load. And then as soon as those rivers leave the mountains and they're now flowing on flatter ground, the water slows down. As the water slows down, these sediments that it's carrying drop out to the bottom of the water column and are therefore deposited. So those river deposits are really being deposited by a slowing down of water. So when we look at this QGE, a lot of what we're looking at, but not all of it, is actually alluvial fans that formed as a result of rivers from the east flowing, dropping lots of sediment, and then essentially causing this one area that we call the Laguna de Santa Rosa to become a low point where more sediments can flow towards. Sediments might also be called alluvium. It's just a fancy word to say sediments. Sediments might also be called landslides, but that's going to be more associated with mountains. When we use the term sediment basin, which is what the Laguna de Santa Rosa is, that's just a way of saying that's the low elevation region where sediment is deposited and where water and sediment accumulate. So why is this important? Because when we look at the Laguna de Santa Rosa, it's not just about the water. Of course, that's what the laguna is, but it's also about the sediments that have been dropped down. Where do they come from? How fast do they flow in? And in many of these cases, when we have these creeks flowing towards the laguna, bringing all the sediment with them, they create what we call sediment plugs. I'm not making that up. That is a term we use. A sediment plug is basically a dam that forms out of sediment. And that dam may not be a perfect dam, but it serves to slow down the water. And as a result, there's more pooling of water. The water doesn't flow as fast, and lakes that may be intermittent or may be permanent are going to form. And we know that the Laguna de Santa Rosa was once a series of what people would call lakes. And we'll see some of those images soon. So how is it that those lakes have drained? Well, they've drained through some natural processes, but it's mostly human intervention that has drained those lakes by clearing sediment plugs, literally taking out natural dams, clearing plant plugs, or where plants would have clogged up the flow of the river, and even creating channels so that the lakes would connect to each other and to the Russian River with a little bit more ease. And that allows the water to flow out and not stay relatively stagnant and behind. So one of the things that I want to look at is really, what evidence do we have that there were once lakes aside from just historical evidence? Where were those lakes? And what evidence do we have for how human construct has changed the way the Laguna looks? And there we go. Okay, so here we have a map. I know you can't read it, that's purposeful. I'm going to be zooming in here. This is a map that I'm going to use for the next couple slides. It's called the Sebastopol 7.5-minute quadrangle. It's a topographic map that geology information has been put on. So we're zooming in. I've showed you a lot of geologic maps so far. Now we're getting more and more detail, because as we move into any one location, what we can do is start analyzing individual rocks. And one of the things I just want to note, and we'll see this in more detail so that you can read it here shortly, everything that's in gray here, that is things that humans have done to the surface of the earth to change sediment on the surface of the earth or channel flow. From this point, basically in our kind of yellow colors, that's all quaternary. That's all sediment that has been laid down in this region, mostly by water flow in really the last 1.2 million years or so, relatively short span of time. And the reason I wanted to give you this picture of like this big map that you can't really read is right here. This is what we call a unit correlation. And the reason I think this is important is the fact that these are all next to each other shows that all of these different forms of sediments and human constructs all occurred overlapping in different places at the same time, showing the complexity of the way that water flows. So I'm going to first zoom into this section, kind of looking at the northern part of the Laguna, where it connects to the Russian River. And then I'm going to expand that and look at this kind of longer section that shows a little bit more of the Laguna, but zooming in helps a lot. So we're still on the same map, just looking at something that we're most interested in. So just to note, what's in green, that's Franciscans. You can see how that comes into play. And what's in brown here, that's Wilson Grove. Wilson Grove Formation is essentially the most recent and last bit of marine deposition. It's literally the sand that was laid down in very shallow marine waters, while the Franciscan Formation and all the surrounding rock was being slowly pulled uplifted out of the sea. Now, the mechanism for uplift, that which did the uplifting, was the San Andreas faults. It's the motion of those plates pushing past each other, but also at least 10% squeezing into each other that allowed for that rock to compress and to lift out of the sea. That compression also led to the formation of faults. And notice here we have the Trenton Thrust Fault. And see those little triangles there? That triangle means this side went up and this side went down. And therefore, the Laguna ends up in a down-dropped block, lower in elevation, perfect for water to settle within. But that Wilson Grove Formation, it's really kind of that last little bit of ocean deposition before the valleys have lifted up out of the ocean, are now technically valleys. We also see within the Wilson Grove intermittent layers of volcanics. So we see some of those volcanic eruptions, like the ash and such, that is actually layered in between the layers of sand. So it's kind of overlapping deposition in a marine setting with the volcanic eruptions. Now, most of those volcanic eruptions would have been occurring to the east of here. Another important one is the QTGE. So that's like this mustard color here. That's the Glen Ellen Formation. The Glen Ellen Formation, also sedimentary, which is why sedimentary rocks are so important for this talk. This was the first layer that was fully the result of river. So where the water deposition was that as a result of terrestrial or land-based rivers, not oceanic or marine setting. So we see this as kind of that transition from ocean to land. And notice that that makes up parts of the ocean, parts of the valley floor. It's really kind of the bottommost valley floor sedimentary deposits post-ocean time. And then QOA, here's an example of QOA right here. This is sediment that was laid down during the time of the mammoths. So we're going to see river deposits. It was a lot wetter climate at that point in time, a lot more water flowing. So there would have been more deposition in this region. So this is kind of think of this as like the second to last chapter of the story of Laguna de Santa Rosa formation. And that way, when I get to this map, we can add on. So there's that QOA. This is the exact QOA I just circled. And when I think of QOA, I think of where were there bodies of water that mammoths would have walked by. That's kind of where we are in the timeline. That's the depositional setting where the sediment is being laid down. And there's no way I'm going over all these Qs. You'd be bored to death in no time flat. So I'm just chose a few because here we're looking at the Laguna de Santa Rosa. Now we have QHA here. There's some right there. Those are alluvial deposits. Again, alluvial, fancy word for sediments. Just think water deposited. This was in an environment where we see sand and silt and gravel, nothing very specific, but definitely water deposited sediments. And notice that this is fairly old. So this is probably the beginning of the Laguna. We're seeing rocks that are probably around 11,000 years old or so, but this might have been the beginning of Laguna de Santa Rosa. It's very hard to put that for sure in a timeline. Now QHB, here's one right there, is QHB, is a basin deposit. And this is really important because basins are low points. They're points where water flows into is not able to flow out of very easily. There's not a great exit point. So it's oftentimes where we have very slow moving or standing water. In my mind, I think of that as close to or is a lake. So everywhere where I see QHB, I know that that is part of the Laguna de Santa Rosa that had a very slow moving river or a full on permanent lake during the early part of what we call the Holocene, or the time that we currently live in. So for those of you who have asked Allison in the past about where those lakes were, the lakes of Santa Rosa of the past, the lakes of Sebastopol of the past, that's what this map does. It gives us a chance to say, well, we have QHB, that's where we had standing water. We have QHAY, here's an example of that one right here. And that is again alluvial deposits, but on the modern floodplain. So whenever you see QHAY, that means that is where the water overflows onto when we have current floods. So I think of that as the high flood potential area. Very handy for modern day flood preparation. And then QHC, that's it's going to be very hard to see because it's narrow. I'll just trace part of it. It's this piece through here. That's the modern day stream channel. That's where the water is flowing, where sediment is depositing right now. It's essentially the constant water flow area. And then all of these gray ones, notice they all say artificial and historical. So these areas, and I'll just show a few. There's an AF right there. Here's another AF, ADF. You kind of have to hunt and pick and just find where they are. You'll see a lot of straight lines. Straight lines are a little less common in nature. So when we see straight lines in a map, I oftentimes suspect humans are going to be involved in that. These are the channels that were dug or modified in the levees, aka low dams that were built, and the bigger dams that were built. These are the structures that humans put in place to change the shape of the laguna. And many of these structures would have been the channels, like through here, that were dug from one of these lakes towards the Russian River to allow the water to leave the lakes and go into the river, thereby draining the lakes. I know you could spend hours on any one map, but there's time for that in the future. So as we start to take a look at the watershed, we're back to the watershed map. Here's Laguna de Santa Rosa. It is essentially in the south and southeast portion of this Russian River portion of the watershed. So water comes into it from the east and also a little bit from the west, but it's mostly from the east. Here I have a couple historical maps that I found that I think are really, really interesting and help us kind of put some aspect of location to these ancient lakes, not even all that ancient, relatively recent lakes. So this bottom left one is from circa 1850. And this is a historical surface hydrology map. And everything you see in this light blue, that is what was referred to as the winter lake. And this was mapped in 1859 is when essentially that was put in place. So during the winter time, the southern part of, it's probably right about through here, the southern part of the Laguna de Santa Rosa would have flooded most rainy winters. And you can see the areas that were building, in fact, all this purple stuff you see, that's all urban building now, how we basically built on what was once a lake. We have, from historical documentation, mostly from newspapers and other written documentation, knowledge of there being permanent bodies of standing water that were dammed by sediment plugs. So natural standing bodies of water that we consider to be lakes. Ballard Lake was closer to like Mark West. The northern Mark West Springs actually was probably closer to up here. And we know that Lake Jonive, which we're going to actually see here on this map, this is again a historical map of 1850 distribution of habitats as types. And where you see this dark blue, that's Lake Jonive. It's basically a wide part of the river that is flowing very slowly. You can see Sebastopol's right here. So it's just north of Sebastopol. There was another lake, Lake Sebring, and I honestly could not figure out from the descriptions exactly where it is. And there is a lot of question in the historical documents about the exact location of these lakes, which is why we turn to our geology maps to try to fill in some of those blanks. Now, why did these lakes get drained? Like, why don't we have these lakes anymore? The lakes, the wetlands were drained or filled, as in drained as in letting the water leave and not letting the water come back in, or filled as in bringing sediment in and filling in the low elevation place so that there was no space for the water to be. It was a combination of those two processes. And it was done very purposely. And it was essentially done in the early to mid 1900s. To prevent mosquitoes, there is documentation from like historical documents describing swarms of mosquitoes. So I think that's probably one of the biggest plus of not having lakes, though there are many people who would like to restore these lakes back to the historical extent. But these were mostly drained or filled to make land agriculturally viable, because at this point in history, land that was considered unusable for human growth, whether that be building or agriculture, was considered useless. We may not agree with that same thought process today, but that was the truth at that point in past. So it wasn't necessarily that they were doing anything bad. It was just the way things were done. So land would have been filled in or drained to make it agriculturally viable, but also to prevent flooding. There's historical documentation that the areas around Laguna de Santa Rosa would have flooded every 3 years or so. So those who lived right on the edge of that flood zone would have been big proponents of draining. We also know for a fact that the communities that lived in this region would have put their sewage directly into a lot of these rivers that would have flowed into the Laguna. So poor sanitation conditions were definitely a consideration, though there's not a lot of historical evidence as to how bad the sewage situation was until there was definitely a drought, I think mid 1900s, when there is documentation of the sewage situation getting really bad because there was a very, very dry winter and therefore sewage concentrated within the laguna. We also know that those that lived along the edge of the laguna, that their land value would have increased by literally increasing the surface area of viable land, because again, wetlands were considered not useful at that point in history. But also some of this filling in was not purposeful. If there was upstream construction, then that construction adjacent to a waterway increases the rate at which sediment is added to the water, and therefore the rate at which deposition occurs within the laguna. And since there's an increase in the rate of deposition, that would fill in that water body. But what we have to remember is that this water body exists because of the fault network that underlays this entire region. So one thing that I just think is super interesting, and maybe in the future when you look at maps, you'll think about this. Up here, we have what we consider a really normal and consistent water drainage type. It's called a dendritic, comes from the same term as dendrite, as in like the dendritic form of neurons in your brain, or dendritic in terms of the way branches of plants grow. It comes from the same term. So this is considered dendritic, very normal, versus here we see that these creeks come into the laguna at nearly a 90-degree angle. That is called a trellis pattern and is always, unless humanly changed by human constructs, it's always a result of fault topography. So if you look at a map and you see trellis patterns, then you should suspect that there are active faulting in that region. So the laguna exists, and the lakes once existed because of the faulting in that region, the way the water flows towards a low point, and then humans made decisions about where they wanted the water to be and where they didn't want the water to be. Cross sections are a really great way to kind of look at this. I cut out like 5 cross sections because I realized I went a little overboard with cross sections when I created this talk. I start with this cross section only because it's relatively easy to comprehend. So here we have the base map over here on the right side. In each of these lines that are drawn, this is the cross section. So think of it as like, think of the base map as like looking down at the top of a cake, but you want to know what layers are within that cake because that will inform you whether or not you want to eat the cake. So this is the cut line. And what we're going to do is we're going to cut along C to C prime. Here's C and here's C prime. And then we're going to cut and look into the layers. And that's exactly what a cross section is. So here's C prime, here's C. The topography is exaggerated. In other words, we use exaggerated topography when this scale here, I'll just make this up, we'll say 1/4 of an inch equals 100 feet, does not equal the scale at the bottom. So exaggerated means the slopes are not accurate. They're exaggerated to make it easier for us to see certain features, like the Bloomfield Fault. Notice this fault here causes uplift on the west side of the laguna. And therefore, we have this higher point through here relative to the low point of the laguna. And then look at all the faults over here. So many faults. A lot of these faults, for example, we have a thrust fault. That thrust fault is based on where we are, probably the Rogers Creek fault, but there's a lot of these unnamed faults. Each of these faults is at least partially responsible for uplift. And what you notice is there's a lot more uplift on the east side. And as a result, there's more erosion on the east side. And because there's more erosion, there's going to be more sediment added to the east side of the valley. And that sediment on the east side of the valley is going to cause the east side of the valley to be slightly higher in elevation. It's just going to be filled in more. And then it also creates a slope for both the sediment and the water to flow to this low point. So it's a combination of more faulting on the east, a little less on the west, more erosion on the east, little less on the west, culminating in the low point that we call Laguna de Santa Rosa. So this is kind of a way to read cross sections if you haven't had the privilege to do so before, because it's helpful to have that little bit of an intro before we come back to this map. Maybe you remember this map. Remember the Sebastopol Fault, and here's another fault. The Rogers Creek Fault, for those who are familiar with that fault, is responsible for the Sonoma Mountains existing. It's a much bigger fault than the other two I just traced. It's over here. And here we have two cross sections. So here's A prime, and B prime. And those connect to these cross sections. Now we get a little more information. So notice we're going to look at the Q is a very, very thin veneer of sediment on the surface. All those surface sediments, even though they seem very voluminous, are actually very thin. We have the Wilson Grove Formation in kind of this buff color. There's that Sebastopol Fault right here. And here's our Sonoma Volcanics. Now, this is a non-exaggerated cross section. So the undulations you see on the surface are a little bit more realistic compared to the actual topography. And so what we look for is right through here, that's the Laguna. And notice that the Laguna is atop Wilson Grove and Petaluma formations. So these are sedimentary layers. Why does that matter? It matters because as the water flows from east to west, some of that water is going to go down into the ground, but it depends on if there's space for the water at depth. So what geologists want to know is there space at depth? We want to be able to say what kind of rock exists down there. And we also want to be able to say, how does water flow through it? So we do crazy things because humans have amazing tools. We take samples out of wells, we do boreholes, and what this map is literally a map going down to say what kind of sediments do we see at depth. I see pretty colors, lots of pretty colors. But more importantly, right through here where the Laguna is, notice that we see a huge variety of sediments. And that's important because we see sediments coming from the east, sediments coming from the west, sediments coming from the south. It's basically a congregation point. A little bit of everything ends up in the Laguna, which is great because it's a perfect place to sample for sediments and use those sediments to read the geologic history of the entire region. I think of Laguna as not only an amazing wetland, but a storehouse of geologic information that if we put more effort into it, we could learn a lot about the last number of millions of years for this general region. So as we start to kind of wrap this up, I only have a couple more things I want to note, but I hope that what I've talked about makes maps like this that are easily available on the internet make a little bit more sense. We know that the Laguna de Santa Rosa exists because of both geologic complexity, lots of faulting, lots of land motion, uplifting, asymmetrical valleys, there's a lot going on, but also anthropogenic things, what humans have done to change the flow of water. We know that the water flows from east and west towards the Laguna. I'm on the left-hand map, flows from both directions, and some of that water also is able to rise up through faults. So this becomes a perfect place for the water to congregate in this region. We also know that the Santa Rosa Plain has a gentle dip that actually causes the water to be able to flow northward to connect to the Russian River, but that humans have built channels, dug channels into the ground to increase that rate of flow. And we've also one of the things that we've done more recently is pump a lot of groundwater out of the ground. That also plays a huge role in the current state of Laguna de Santa Rosa, because if we're taking water out of the depths, it's going to lower the surface level. So here's the way I like to think about this. It's like if you have a bowl of cereal, you're going to put whatever cereal you want, and then you're going to put whatever milk you want in there. It can be water or orange juice, whatever your druthers may be. So you can see you're going to fill it up enough that you have your liquid all the way to the top, that all your cereal is buried. That's kind of like what this laguna is. Now put a straw in it. Nobody eats their cereal with a straw, I know that. And then you're just going to start drinking that milk, that liquid out. And so it's going to be pulling the liquid from the bottom, but the surface level of that liquid is going to drop down. It's thereby going to cause the surface of the cereal, which represents the sediment, to become visible. And that's part of the modern day reason that we have lower water levels in Laguna, in addition to drought, in addition to the channels that have been dug to purposely drain the Laguna. Our use of groundwater does play a role. And we can see here in this map, here's Laguna de Santa Rosa, all of these interesting looking trapezoidal things, those are wells that samples are taken from. And I put it in here because you can see there's a lot of wells in that area, and that's not necessarily a bad thing. It just means that's another way we're using the water that used to just pool upon the surface. There's another thing I want to note while I still have a chance to do so, because I love my natural disasters. That's just the way I am. And anytime we're talking about a sedimentary basin, a basin where water settles within and sediment settles within, then we also have very specific hazards that we need to be aware of. And that's very plain in these maps. So up here, check mark, this is a landslide hazard map. It's from a website called ABAG, ABAG, Association of Bay Area Governments. They have a great hazard portion to their website. And right through here, this is Laguna de Santa Rosa. So notice there's no landslides. It's flat land. Woohoo! That's one hazard that the Laguna is not going to have to worry about all that much. But whenever there is a lack of landslides, there is definitely flooding. So notice the same area. So this is, I'm just going to trace this in to help you figure out where we are. This is the Russian River. This is the Russian River. So that same arc that I just drew. And everything we see in blue, that is the flood potential for the Laguna de Santa Rosa. If there's not landslides, there's flooding. That's just the way slopes work. The dark blue area says it's a 100-year flood. 100-year flood would be better termed. There is a 0.1% chance of flooding every year, because using the term 100-year flood can be misguiding, because it makes some people think that, well, it flooded last year, it's not going to flood for 100 years. It's really better stated statistically. There's a 0.1% chance of flooding every year. That chance may increase in the future as climate changes, but even more so, any place where you have lots and lots of sediment building up. Here's Russian River. Again, I'm going to do that same trace. Here we have Laguna de Santa Rosa. We also end up with earthquake liquefaction susceptibility. And this is a little experiment that was done. So you have sand, and they're going to essentially add a vibration to it. So there's a little house sitting on the sand. Think of that sand as like the sediment of Laguna de Santa Rosa. Now, once that earthquake vibration is there, then essentially the sediment behaves like a liquid while the vibration is present, and surface features can sink down into it. We call it liquefaction because that which was solid starts behaving like a liquid. This is especially going to be the case in valleys and marshes. And so there's no way I can talk about a wetland or a marsh without talking about the liquefaction possibility, because it's a possibility. In fact, we would say it's a very high possibility. So do you have an emergency kit packed? Anyone who's seen my website and gone to my talks knows that I'm a big proponent of having an emergency kit packed, because there's no way we can warn you when the earthquake can occur. You just will have to be ready when it does. There are still a few unanswered questions about the Laguna de Santa Rosa. Like, why doesn't the Laguna flow south? I mean, okay, At this point in history, the south part of the valley is just a little higher in elevation than the north side. But really, the Russian River is weird. I mean, I'm going to trace it. What kind of river does this? This is some weird flow pattern for a river. Most rivers just follow valleys, so I'll kind of trace what we would expect the river to do and to head out towards San Pablo Bay. But the fact that the river takes this 90-degree turn to the west is really because of faulting in this area. There is a hypothesis that we cannot prove at this point because we do not have the data to do so that suggests that the Laguna de Santa Rosa may have once flowed south through Petaluma to San Pablo Bay. But as we've seen with the complexity of these geologic maps, it's going to be really, really hard to get the evidence for that, especially since faults keep moving things around. What we understand for this region is that because this is still an active tectonic boundary, the San Andreas fault system, which includes hundreds, thousands of faults, there will be more earthquakes in the future. It's a guarantee, and that will continue to increase the elevation of this area, but not equally. So one earthquake might cause the east side of the valley to go up a little bit more, and the west side might actually drop a little bit, or maybe it goes up a little bit less. It's impossible for us to say, but we expect topographic differences in the future due to earthquakes. We also know that weathering and erosion from especially rain is going to erode mountain elevation, and that's going to carry, the rivers are going to carry that sediment into the laguna. So we're going to always have more sediment heading towards the laguna. The question is whether or not that sediment acts like a plug and decreases the rate of water flow, because those sediments always accumulate in valleys and rivers. And some of that water is going to infiltrate into the groundwater basins. And here we have a groundwater basins map, and I put it on here just for one reason. The groundwater basins map do not perfectly overlap with a watershed map at all. A watershed map is showing how water flows upon the surface of the earth. It's a surface flow map. Whereas a groundwater basin map is really showing how water congregates and flows at depth. They only loosely reflect each other, and it's very different from one region to another. And we also need to expect that with future climate change, what I would term climate disruption as a result of human activity, we are going to see changes in hydrologic features. We're going to see years of more water and years of less water. Droughts will be deeper. This has been known in climatological circles for several decades now. So we should expect that the Laguna is very likely to be impacted by what is in our near future. And we all agree the Laguna de Santa Rosa it's special. It is unique. It is something that we should take care of. And yet when you look at Santa Rosa maps or California maps, notice it's not even on there. It is so small that on this California hydrologic map, they didn't even bother to put any of the Laguna de Santa Rosa, much less the Petaluma River, on there. It is small, it is unique, and because it's small, it means that we need to take care of it with a little bit more focus, because this is the water that accumulates in our region. So in the future, we expect topographic changes and earthquakes. We expect years of greater precipitation associated with flooding, very important source for groundwater, so that's not necessarily a bad thing. But we also expect years of drought and flood and the deposition from landslides and fire debris. What might be really interesting, and I keep hoping someone's going to take on this project, it won't be me, is that future scientific studies will be able to reveal historic wildfire patterns by literally digging for layers of charcoal within the Laguna de Santa Rosa, because if fires occurred to the east, then that charcoal would have washed into the laguna and become part of those sedimentary layers, that we could learn a lot about historic flooding and historic wildfires just by using the Laguna de Santa Rosa as our study area, because this is a low point in our topography overall. This topographic map really shows why water flows in this direction. No, look it, Allison, my timing was perfect. That never happens. So for those of you who are interested, my website is appreciatingearth.com. I do geology walks and talks about once every month or two. I do a geology walk out in nature and do my spiel about all the geology we can see. I have a newsletter, and I also want to give a shout out that Rebecca Perlroth of Santa Rosa Junior College is doing geology of the Mayacamas with the Pepperwood Preserve. So that's going to be focusing on the geology of the mountains to the east of Laguna. And it's a two-part. There's a talk, and then there's a actual walk on the preserve. But I always like to give that little shout out because there's no such thing as enough geology. Allison, I am ready for questions if you would like.
Well, I will give you a round of applause since you can only see me. I just learned so much about the Laguna. I really appreciate all of that information and all those maps. It was really helpful to visualize so many things that I've read about, but I haven't really been able to put in my mind because I haven't seen a good visual. So thank you so much. It was excellent. The chat is exploding with lots of thank yous and compliments. We do have some questions, and I will try to go kind of in chronological order here. So moving back in time, how big is the Franciscan complex, and where can you find it along the California coast? Do you know the most northern and southern border?
That is a big question, and the answer is basically everywhere. I'm going to go back. If this makes you dizzy, close your eyes for a moment. There we go. I went way too far back, and PowerPoint is freaked out. Okay. I'm looking for, there we go, the Santa Rosa sheet. So we call it the Santa Rosa geology sheet. There's also the topographic. It's a 1x2 degree sheet. And I bring this one up because it gives you pretty good region area. Everything you see in green is Franciscan. There's a lot. In fact, if you were to parachute out of a plane onto the coastal mountains, there is a really high chance you're going to land on Franciscan. I would say, I'm going to totally guess on a number here. I'm saying over 80% of the coastal mountains is Franciscan. So you can get that all the way up to Point Arena and all the way south towards, I'd say almost as far as the transverse range, which most people know as the Grapevine. It's what the I-5 goes over. So it's the majority of the Central California coast is going to be superficially Franciscan and in all cases underlain by Franciscan.
Wow. Yeah, that was a missing piece, I think, in my geologic knowledge of how this area formed. That accretionary wedge was something I was missing. Great, thank you for clarifying. More kudos, shout outs coming in the chat and more questions. Do the trellis stream patterns tend to be perpendicular to a fault or just in the general area where faults are occurring?
They tend to be both parallel and perpendicular to faults, and oftentimes the longer parallel part of it, I'm going to see if I can make my way there, is along a fault. So yeah, here we go. Change my color to make it a little bit easier. So this long part of the trellis, I think it was like the vertical part of the trellis, even though it's technically not vertical, that's almost always parallel to the fault itself, if not directly on top of the fault. And then the small pieces tend to be perpendicular to the fault.
Okay, great. Thank you. One question just came in that I want to make sure we hit because there might be others wondering this too. Someone says we live nearby on the Santa Rosa Plain. Can you suggest where to find more of this type of information on the Santa Rosa Plain and how it works within the Laguna? What's your favorite resources that you use to find this information?
There's some hydrologic papers, but they're dense. Like they're a little bit to take in sometimes. I have a few resources on my website that I think are oftentimes a good starting point. If you are looking for a very like specific document, then there are two hydrologic papers that I would recommend. One was by Robert Ford, but I think that one's from like the 70s. And then a second one is the Santa Rosa sub-basin. I'd have to look up the name of that one. It's like over 100 pages and it makes my brain hurt. And I don't have it posted up here right now. I will post that this week so that those who are interested can make use of it. A lot of like the well maps and the map I showed with the A-B cross section, that comes from that paper.
Excellent.
I say good luck to anyone who chooses to read that.
Well, I will certainly put a link to your resources page on your website in the follow-up email, and we can write the names, authors, titles of those papers in that follow-up email as well. So thank you for that. There's been some questions coming in about the aquifers and aquifer recharge. Gosh, yeah, there's quite a few. So I'll just try to hit some of the more general ones. Is the aquifer to the west of the Sebastopol Fault recharged only from the west, or is it also recharged from the area to the east of the Laguna? So if you know, I'm not exactly sure where that is, but.
I'm not sure if anyone can answer that question completely, but based on, so when we think of how water flows, it's going to flow from high to low. And then the way that water flows at depth is going to be pseudo parallel to that. So we know surface water is going to do this, and groundwater is going to be doing something very similar to that. So the main recharge zone is going to be in the Wilson Grove Formation, which is the brown area. And it's going to flow to depth. And then what happens is it comes in contact with the Sebastopol Fault, and water is always going to take the easiest path of flow. And the easiest path of flow is actually going to be up or down along the fault, especially since it's meeting a hydrologic pressure of water flowing from east to west. There's not going to be a lot of ease for that water to move in the opposite direction. It's like going down a freeway in the wrong direction. It's not going to be easy. So most of the water is probably going to move along the Sebastopol Fault. Some of it's even going to be added to the Laguna because it rises along the fault.
Okay, so that kind of gets at this question, the second piece of this. Someone asked, do the current quaternary soils allow sufficient infiltration that allowing broader winter flooding would promote relevant amounts of managed aquifer recharge? And I will, broader winter flooding. It does still flood in the winter, but do the soils allow for sufficient infiltration? Is there any way to know if that is happening?
It depends a lot on the individual soil. And one of the things I avoided in this talk is looking at a soil map, because if you thought any of the maps we looked at are complex, it's just a lot of lines and like letters all over the place. There's so many different kinds of soils. So to kind of answer the question in a sidelong way, when there's a lot of clay in the soil, that's going to impede the rate of flow. And that's important because all of the volcanic rocks over here have a lot of feldspar, and feldspar is a very common mineral. It's found in all kinds of rocks, but it's very plentiful in these rocks. And feldspar breaks down to weathers into clay. So it is the source of the huge amount of clay that we have in this region. For those of you who have cracks in your walls and your ceiling, and those cracks annoy you like no other, you can blame the clay for that. And it's mostly derived from these volcanic rocks. So whether or not the water is able to infiltrate to depth is dependent on the soil and on the ability for water to flow through the rock beneath that soil. But it's also very much dependent on the clay within that soil and atop the soil if clay has been actually laid on top, and droughts. Because if you think of soil and sediment as being like a sponge, Sponges can be very good at letting water flow through them and absorbing that water until you take that sponge that you used outside and you leave it outside in the sunshine for like 4 months. And then what happens when you try to get that sponge wet? Water splashes right off of it. Like you have to have it soaking in water for hours to get it to take water back in, because it literally bakes it to a point of not being able to infiltrate. So part of the worry of coming out of a drought, hopefully we're coming out of a drought, part of that worry is that surfaces have been baked really, really dry. And so they're going to be less willing to take water. Our infiltration capacity is slower.
Right.
So I think like don't want flooding this year.
Yeah.
But yes, I think it would be beneficial in the long run if we took care of surface infiltration conditions to have areas of more flooding, specifically more water retention, so that the water had time to settle in.
That is interesting. That is an aspect of the drought that I haven't thought that much about. Thank you. Okay, this question is fascinating. Thank you, Kelsey, for asking. Foster and Rolling, that looks like some authors paper from 2013. They estimate that that CO2 at current levels are associated with 20 to 30 meters. Is that right? 20 to 30 meters of sea level rise. The Laguna is about 15 meters above sea level. How long do you think it will take for the West Antarctic ice sheet in Greenland to melt? And then what would happen in this scenario? What would happen to the geology of the Laguna if it was to become an estuary of some sort?
Wow, that is a fascinating question. The truth is, I have no way of putting a timeline to that aside from what climatologists predict, but I'd like to note that I've been studying climatology for 20 years, and every estimate that I have read in that 20 years has happened faster than we expected. So that's definitely not a positive right there. There was a study of the Petaluma River that came out recently that looks at how most of the Petaluma marsh area will actually be tidal flats by the year 2050 to 2070.
Wow.
Which it's pretty fast. And that's not saying that the Greenland ice sheet has completely melted to make that happen. It's just a relatively fast rate of rise due to the expected rate of ice melt. As far as the Laguna goes, though, one of the things that is really important about the Laguna that I kind of just didn't get to because I had to take slides out of just being realistic here. There we go. Here is the southern boundary of the watershed. And then the Petaluma watershed is south of that. And the reason the boundary crosses over the valley, which is very rare, usually watershed boundaries are actually at the top of mountains. Mm-hmm. Because, for example, here at the top of this mountain, water flows this way or it flows this way. And even here, water flows this way or this way because of the topographic change. But this is a valley. But anyone who's ever been on 101 or the Petaluma Hill Road knows that when you approach Pengrove, you go up and over. That's the Pengrove uplift. It is due to faulting. So the water level would have to go high enough, the sea level would have to go high enough to actually top over the Pengrove uplift to flood from San Pablo Bay all the way up to Laguna. So I'm not actually all that concerned with sea level rise having a direct inland flooding impact on Laguna because it would have to be significantly more intense to literally make it over that Pengrove uplift, in which case we have so many more problems to think about at that point. Right. I'm not going to even worry about what's happening as far as flooding at that point.
Right. It is fascinating to make that connection, though, that it's just that uplift, like separate, otherwise we are on that level and we're just separated by that little uplift from much sooner effects of sea level rise, which is not something I associate with this area at all. So
exactly.
Fascinating. We have just 5 minutes left. So I just wanted to clarify this question. There was a couple questions about the faults, so maybe you can answer quickly. how active are these faults? Is there like an active earthquake risk from the faults, not the San Andreas, but the faults specifically close to in the Laguna watershed? And then there's a question about the Rogers Creek fault. Someone has heard that the Rogers Creek fault has at depth rocks that are magnetically oriented, such that in an earthquake, the rocks magnetically resist movement until a sudden release.
I would be very interested in the source of that, because I don't know how we would know that. Other than doing like borehole studies, which maybe have been done. I certainly have not read every paper out there. As far as earthquake potential, there's essentially a 67% chance of an earthquake of magnitude 6.7 or greater happening in the Bay Area region by the year, I think, 2032. I'm trying to remember every number on a map right now. The fault line, so what they do is they like highlight certain fault lines and say, okay, of that 67%, like 20 something percent of that 67% is actually Rogers Creek. Rogers Creek fault has the highest potential of producing a large earthquake. That will affect the entire Santa Rosa region. San Andreas has the second highest chance of that. They're both, just think of them as big faults in the system, like the bigger threads in a scarf. And then there's a number of other faults in the region that are part of this overall number. But then there was like, I'm trying to remember what it was. It's like 11% of that was the earthquake might occur on any of the other faults that we have not specifically put on that map. The Sebastopol fault and the Trenton Ridge fault, all of those are going to fall within that kind of category of, it's not one of the main faults we're most concerned with, but we can't ignore it. Even if you think of the Napa earthquake of what was that, 2014, the Napa earthquake, that was not actually, that was part of that other fault scenario. It wasn't one of the main faults that we thought were going to have an earthquake. In the case of Rogers Creek having an earthquake, regardless of the nature of the rocks at depth, the plates are moving. The rocks are moving. Essentially, I'll do it this way. Think of it like this. My arms have already moved. There is a point at which my fingers are going to have to move apart from each other to catch up with the motion. And that's what happens with an earthquake, is essentially it's like so much motion is taken up and then everything else has to catch up. So it doesn't matter what the resistance at depth is. There will always be an earthquake to allow for rocks to catch up with the motion that's already taken place tectonically.
Right.
I just hope it doesn't happen in my lifetime. Statistically, that's unlikely, but I just don't want it to happen in my lifetime.
Oh, and one last question. I've always been trying to answer this question in my family. Where would you consider the safest place to live in Sonoma County? In my family, we've put this like in the United States, but where would you consider the safest place to live in Sonoma County away from natural disasters based on your geologic knowledge? And we won't quote you on this.
I know. I'm like, okay, so if you're a geologist, this is the way you think about it. You want to build your house directly on solid bedrock. So if I could build somewhere where I can literally drill the foundation of my house directly into coherent and has not had any landsliding recently, Sonoma volcanics, that's what I would do.
Great. You should look at the
If I was in
geologic map.
If I was in San Francisco, I'd want to live on one of the hills, because all those hills in San Francisco, most of those are like solid bedrock. If you can drill your foundation directly into solid bedrock so that you're not on top of the sediments, that is your key. There's no place in Sonoma County that is not going to shake like a bowl full of jelly at some point. I just want my foundation to be part of the rock, like the solid rock, and mine is not.
Right.
I'm in basically a worst case scenario. So yes, I have thought about this question many, many times. And the truth is, I have yet to find a perfect place.
Yeah, it is a really hard question to answer nowadays. And certainly in the state of California, feels hard to avoid something, but it's interesting to hear from a geologic perspective.
And my suggestion is to choose which natural hazard you're willing to live with. Rather than trying to avoid them all, it's not possible. Just choose which one you're willing to live with. I prefer volcanoes and earthquakes. I'll take those. I do not want hurricanes and tornadoes. I'm not okay with that.
Yep. Pick your natural disaster. Well, thank you again so much, Nicole. Oh my gosh, we just have so many compliments. Someone said, thank you, so informative and easy to follow along without a science degree, which I will echo, having gotten lost in many geology lessons in the past. Lots of love for the maps, the visual aids. Thank you for sharing your expertise with us. And again, reminder that this was recorded. You'll receive a link to the recording in your email in the next couple days. Thank you all for joining us. Big round of applause again to you, Nicole. And everyone have a good evening.
Thank you.
Bye.